There are many kinds of dynamical systems. Some are complicated, others are not. Watch this vector field in space. The field depends on a parameter a. Let's start by choosing a equal to 0.3 and watch what happens for a large number of initial conditions. After a while, they are all attracted to a single periodic trajectory. No chaos here. There certainly is an SRB measure, as all initial conditions wind up moving along a closed curve. Let's slowly change the parameter a. We see that, for a equal to 0.335, the periodic trajectory splits apart. Still no chaos, but now the periodic trajectory is about twice as long. And then, for a equal to 0.38, the attracting trajectory doubles a second time. Then things speed up. For a equal to 0.405, the attractor is complicated and chaotic. But the surprise is, if we continue to increase the parameter a, sometimes, without warning, the chaotic dynamics simplify, returning to just a single periodic orbit. How can we understand these bifurcations? What is the most common behavior in nature? Chaotic? Non-chaotic? It is not clear at all. For centuries, we had no idea that chaos could exist. Today, we see it everywhere. For each value of a, we can record how the attractor meets a plane. We draw the intersection in red. As the parameter a varies, we obtain a picture that looks like a piece of lace. This is called a bifurcation diagram. Very pretty, but not so easy to understand. Here are some other dynamical systems. Mathematicians seek to establish results that are universal. But they often start by studying examples. They then hope that what they see in the simple examples will hold in all cases. Recall the idea of Lorentz and the Sinai-Ruel-Bowen, or SRB, measure. The proportion of time that a trajectory spends in a ball converges to a limit that does not depend on the initial condition. Is it reasonable to expect that this always happens? That would be too nice. So, unfortunately, it is not true, as we will see in a small example discovered by Bowen. Watch this vector field in the plane. There are 3 points of equilibrium. a trajectory starts, after a while, it approaches a point of equilibrium and then moves on to the other one. When it approaches an equilibrium, it slows down and remains near that spot for a while. Then it speeds up towards the other equilibrium and remains there even longer. Back it goes to the first equilibrium, where there is an even longer delay, and so on. Consider the little green disk. Let's keep track of the transit time spent in this disk. Well, the trajectory stays there for such a long period that the proportion of the time is close to 100%. Then we leave the disk for an even longer period of time, so the proportion of time in the green disk falls nearly to 0. Then it climbs back up to nearly 100% and then falls back to 0, and so forth. As you see, there is no convergence, so there is no Sinai-Ruel-Bowen measure. What should we do? Shall we abandon this idea? Say that Lorenz was mistaken? Well, no. The example we have just seen is very special. If we change the vector field just a little, like this, then the problem goes away. The new trajectories travel in the plane and eventually approach a periodic trajectory. So, statistically, everything now behaves periodically. The new vector field has a Sinai-Ruel-Bowen measure. So the question is whether these measures show up not for all dynamical systems, but for most dynamical systems. Again, we must temper our enthusiasm. Watch this vector field. Here is a trajectory. All is well. It accumulates on a butterfly, as we have seen before. As the initial condition moves slowly along the blue axis, everything behaves as it should. The trajectory always accumulates on the orange attractor, even if it takes a little while to get there. We can easily check that the statistics have not changed. But, all of a sudden, without warning, a surprise. The trajectory accumulates elsewhere, on another attractor that has nothing to do with the first. Space appears to be split into two regions. If one starts with a point in the first region, the trajectory accumulates on the orange attractor. If we start in the second region, we end up at the green attractor. In other words, there is no SRB measure since the long-term behavior depends on the initial condition. In fact, there are two SRB measures. For certain initial conditions, statistics follow the first measure. For other initial conditions, the second. In the 1990s, the Brazilian mathematician Jacob Pallas formulated a whole set of problems that, if resolved, would allow for a global vision of chaos. One of these says that the situation we have just encountered should be typical. In all dimensions, A typical vector field should have only a finite number of attractors. A typical initial condition should be drawn to one of these attractors. Each attractor should have a Sinai-Luell-Bowen measure that describes the asymptotic statistics of the typical trajectories that fall into that attractor. A whole group of mathematicians is hard at work on these conjectures, and they are being solved methodically, bit by bit. A global picture seems to be emerging. Is this picture too optimistic? Time will tell. Today, we no longer think of determinism as the evolution of an individual trajectory, but rather as the evolution of a whole collection. Sensitivity of trajectories to initial conditions is compensated for by a kind of statistic stability of the collection of trajectories. Did Buffon in 1783 not foresee this when he wrote this magnificent sentence about a complex and chaotic world that one has to try and understand globally?
Everything happens because with time everything meets, and in the free range of spaces and in the continuous succession of movement, all matter is stirred, any form given, all figures printed, so everything is coming or going, all is joined or running away, all is combined or opposed. Everything happens or is destroyed by relative or contrary forces that are the only constants. And balancing without harm, they animate the universe and make it into a theater with ever new scenes and objects incessantly reborn.